Hello, my name is Soledad. I'm an assistant professor in applied math and statistics at Johns Hopkins University. And it is my pleasure to be speaking at the LatinX and AI workshop this year. And this is my email address. I'm sorry I'm not there in person, but if you want to contact me, we can discuss it during the Q&A, or you can reach out to me. Before I start with the research part of this talk, I wanted to talk about Uruguay, where I come from. It's a very small country in South America, which is famous, or maybe infamous, for football. And it's a very nice place. If you haven't visited, I highly recommend it. Of course, I'm biased, but I love it. It's a very nice place. And a reason to go would be that next year, Uruguay is going to be hosting a big event for AI in Latin America, which is this event called KIPU 2023. It has had an in-person event in 2019, and it has had many online events during 2020 and 2021 for obvious reasons. And you see there's a website where that many of these talks are hosted, so you can go check them out. And next year, the lineup of speakers that are going to be in person is great. So, for instance, Kim Yun Cho is going to be there, Sami Bengio, Rachel Ward, Joan Bruna, etc. So, I suggest you check it out, and also for next events, just keep it in mind. And yeah, that's a good reason to go to Uruguay. And also another advertisement is this cibercoloquio latinoamericano de matemáticas, which is just like virtual talks, but they are in Spanish and Portuguese. And we have this YouTube channel with many of these talks. We have like a monthly event, which is online over Zoom, but also we put together these talks in this YouTube channel, and they're for like broader math, not just machine learning, topology, geometry, number theory, etc. And these talks are very nice by very well-known mathematicians. So I encourage you to check it out if you want to see talks in Spanish or Portuguese, or you want to recommend that to students or friends. So that's for the advertisement part of the talk. But since this is a social event, I thought that it made sense to do this. So I'm going to start the research part of the talk by a motivation that is well known to all of you, deep learning. So you know that in deep learning, we use very overparameterized models. We have way more parameters than data points. And that implies that many functions in the hypothesis class can fit data quite well. So the question is, how do you choose the right function in the hypothesis class that actually performs well? And with that, I mean that it generalizes well. So it performs well not only on the training data, but also in test data that it hasn't seen during training. And so the question is how we define the hypothesis class of functions with the correct inductive bias for the problem, meaning that local optimization will converge to a good solution with good generalization properties. And so in order to do that, people design many class of functions, many architectures justified on the underlying problem that it aims to solve. So in particular, I'm going to focus on these two architectures, convolutional neural networks and graph neural networks, which is a class of architectures. So in convolutional neural networks, which is before transformers, is the preferred architecture for image processing. What this class of functions does is apply the same convolutional filters in many locations of the image. and that results on a translation equivariant architecture. So meaning that the filters applied in different locations make that the representations that you learn from these images are equivariant with respect to translations. If you design the filters so that they're also rotationally invariant, then you can have rotation equivariant architectures as well. And that is a natural kind of inductive biases for image processing. GNNs, on the other hand, what they do is they learn functions on graphs that are independent of the choice of representation of the graph as an adjacency matrix. So say I have this graph, I have many ways to express this graph as an adjacency matrix, but the function that I learn of this graph, which is maybe a labeling on the nodes, is independent of that choice. And that corresponds to architectures that are invariant or equivariant with respect to the action by permutations. So for instance, message passing neural network do that, and almost all graph neural network architectures have that specific property. So I'm not going to talk about neural networks, but it's a very good motivating example of what we want with equivariant machine learning. And basically what we want is we want to exploit the symmetries that problems have. And in the physical sciences, one can identify two types of symmetries, what I call active symmetries, which are symmetries that are observed regularities of the physics. For instance, symmetries that have to do with a physical system that has conservation of energy, which can also be seen as a time translation symmetry. And the connection between conservation quantities and symmetries of the physical law are given by a theorem by Emmy Noether at the beginning of the 20th century. Other symmetries that are less apparent are symmetries that have to do with the choice of the mathematical representation of the objects. So the example that I gave you before, the graph neural networks have many ways to represent a graph as a matrix, and that gives an underlying symmetry that the problem has. And the same thing can happen with any physical object, actually. Like if you have a physical problem, you write the coordinates of your problem in some coordinate system, and then that is not an intrinsic representation of the object. You can change the units, you can change the coordinates, and then you'll have a different representation. And the physical world doesn't really care about the mathematical choices that you use to describe it. So you should, your machine learning models could be independent of these mathematical choices that one does, and that would reduce the dimension of the problem if one can actually implement it and make it, it would be something that allows you to learn from a smaller amount of data, just because if you have an object and you have 10 ways to represent it, then you need to learn like a function on these 10 objects. But if you can compress them into just one, then you only need, say, one sample to represent that, like intuitively. So the claim is that machine learning and data science methods should be consistent with these symmetries, and that would allow us to have smaller models that can work with a small amount of data, and also that kind of like incorporate the correct inductive bias and maybe work better. And this is a very active area of research. So finally, the last piece of motivation for this problem is this is the first sentence of this book, Modern Classical Physics, but Blanford and Thorne, that says that the laws of physics must all be expressible as geometric, so coordinate independent and reference frame independent relationships between geometric objects, which are scalars, vectors, and tensors that represent physical entities. So I'm going to explain how we can use that idea of like representation of coordinate independent objects to design principal machine learning models that obey certain physical properties. And that's basically the main part of my talk. So I'm just going to define invariance and equivariance. So say that I have a group, and this group acts on a data set X. We say that a function is invariant if when we apply the group transformation to the input, the function doesn't change. So for instance, in this example, we have this picture, and if we apply a rotation of the picture, the classification value doesn't change. And equivariant, if the group also acts on the codomain, then we say that a function is equivariant if every time that we act in the input by this group action, then you act in the output by the same group action or by the same group. So for instance, say that we have this particle simulation and we want to predict positions and velocities of my particles after a certain amount of time, then if I apply a rotation to the input, then the outputs rotate in the same way, and that's an equivariant function. So what does equivariant machine learning do? Basically, what it does is it parameterizes the hypothesis class of functions so that all the functions in that class are approximate, invariant, or equivariant. So basically, for every choice of parameters, the corresponding function has that property. And therefore, you're optimizing in the space of invariant or equivariant functions. And then that reduces the dimension of the hypothesis class of functions, which doesn't imply that you reduce the size of the parameterization, but that's a different thing to discuss later. Okay, so the applications, as I mentioned before, to this problem have to do with, for instance, you can apply it to images or like vector fields, fluid dynamics, particles. Another application of equivariant machine learning is graphs, as we discussed before. And the thing that I'm going to focus on today is the application of equivariant machine learning to particle systems. So that includes the example of protein folding, for instance, where people use equivariant transformers to design these models. And I'm just going to describe the mathematical description of how to parameterize equivariant functions and how to make that efficient. So basically in this talk, in the last 15 minutes of this talk, I'm going to describe how to implement equivariant models on particle systems. And with that, I mean rotation, translation, and permutation equivariant functions, and also scaling invariant functions or equivariant functions. And I have a few applications that I'll briefly mention. One is a toy example, just to explain some concepts. And then there's applications to cosmology and vegetation dynamics. So in practice, symmetries are implemented basically with data augmentation, just transform the data set to add transform versions of the training set and corresponding labels. And then that is a good way to get many things. Data augmentation is used not just for implementing equivariance, but for many other purposes, and that's one way to do it. Another way to implement symmetries is by use the fact that many of these symmetries correspond to conserved quantities, and so you can add a penalization in the objective that makes these quantities likely to be conserved, and that is translated into some symmetries. But what I'm going to discuss today is architectural design, which is restrict the class of functions to functions that satisfy the symmetries. And the better is that when this class of functions are actually universal, so they can approximate any equivariant function, which is something that can be done for some groups, but not efficiently for all groups. And there's many ways people do it, and I would like to discuss, or comment. There's a lot of work by Taco Cohen in this space, like a lot. You can look at his papers from 2016 to today. He had done many of the foundational work in this area. There's also a lot of work by Risi Kondor and and Maron as well, where they show many ways of present the equivariant machine learning in terms of irreducible representations. There's a very nice paper by Finzi and collaborators in ICML 2021, I think, where they have a different way of expressing the equivariant networks with constraints. And so they don't actually need the irreducible representations. And I'm going to focus on my work, which is using invariant theory to parameterize the space of invariant functions. So one natural way to do this, and that's, I think, one of the first ways that people have done it, and you can look at the papers by Maron and Condor, is basically say, okay, so I want to implement a class of functions that is equivariant. And so what they do is they say, I'm going to take a feed-forward neural network, which is a composition of linear functions with nonlinear activations, and I'm going to make the linear functions to be equivariant, and then I'm going to design the activation functions so that they don't break the equivariance. The issue with these kind of architectures is that when you consider linear functions that also have these, like, if a linear function so that if I rotate the input, the output rotates as well, then there's not that many linear functions that have that property. So actually, in that case, you will have only like the identity, multiples of the identity. So then that's not really something very expressive. So then what they say is actually, okay, we're going to extend this idea to tensors, and maybe instead of looking at linear equivariant functions on vectors, we're just going to consider the tensor of the input with itself k times, and then parameterize the linear equivariant functions from tensor products of the input space to tensor products of the output space. And that is kind of like, intuitively, you can think of it as, instead of parameterizing the linear equivariant functions, I'm parameterizing the polynomial equivariant functions of degree k. And so then what they do is, okay, in order to do that, they have to extend the action of the group to tensors, and they do it in the natural way, which is like, is a tensor product of the group acting in each of the vectors that you are taking the product of. And so the next question is like, how do you parameterize the linear functions from this space to that space? And typically what they do is they use representation theory in order to do that. They say, well, if I can decompose this group, or basically this space and this space, in the irreducible representations of the group in that space, then once that they have the irreducible representations, there is a natural way to parameterize the equivariant functions, which requires computing something called the Clebsch-Gordon coefficients. And in order to write this, the composition of the space in the irreducible representations, and that basically is what they do. They just take the representations and then they compose the irreducibles and then use that to parameterize the equivariant functions. So that is technical, like you need to learn how to do this decomposition, but it works, and people have used it successfully recently. The approach that I'm going to describe is an approach based on invariant theory, and this is easier to implement, but it doesn't really work for all groups. It only works for certain simple E groups, whereas the irreducible representations approach could be, in principle, written for any group. And basically, the idea is that for these simple E groups, like the orthogonal group or rotations or Lorentz groups that are based on some quadratic form, which the invariants are well known, one can look at what is the first fundamental theorem of invariant theory for that group. So for instance, in this case, we have that, say that we have this particle system over here, and basically, and say that we want to, so we can represent this particle system as n vectors in Rd. So here n vectors in R3. And we want to learn a scalar function of that particle system that is invariant with respect to rotations, say, or orthogonal transformations, actually. So rotations and reflections. So the fundamental theorem says that a function has that property if and only if it is a function of the inner products of the input vectors. So here we have the Rd to the n, so n vectors in Rd, and we can map these n vectors in Rd using this featuring map that basically computes the gram matrices of these vectors, so the matrices of the inner products. And then any function that go from n vectors in Rd to R that is invariant factors through this representation. So it can be written as a function of the inner products. And any function that is written in terms of the inner products is also invariant. And that's easier to see because if you take these vectors and you rotate every one of them, the inner products don't change. So that's a trivial direction. And that is a characterization for the orthogonal group, but similar characterizations hold for the Lorentz group, rotation, symplectic group, and unitary groups, just simple groups. Using this characterization that tells you how all invariant functions look like, then we can use it to see how all equivariant functions look like. And the characterization tells you that if you have a function that takes n vectors in Rd and outputs a vector in Rd, this function is OD equivariant if and only if the function is a linear combination of the input vectors. So these are the input vectors, where the coefficient functions are OD invariant scalar functions. So functions of the inner products, as we saw in the previous slide. And this gives you one of these functions that output a vector in Rd. But if you want to do like the prediction of the particle system that we had before, then you can just learn n independent functions, like to predict each of the particles. This suggests an architecture for this model that is an equivariant architecture that is very simple to explain. You take the input vectors and then you compute the scalar products of the input vectors. That gives you invariant features. And then you learn a function. You learn n functions, f1 through fn, which are these coefficient functions that are functions of the scalars. And then the output is going to be the corresponding linear combination like we have here. And this architecture is universal. It can express any invariant function because the invariant polynomials are a generating set for the algebra of invariant polynomials. The inner products are a generating set for the algebra of invariant polynomials. And this idea is easy to implement as equivariant self-attention. So a similar formulation exists for SOD, but instead of just being so SOD is rotations in dimension D. Instead of asking that is a linear combination of the inputs, you may have other vectors that go into play in the parametrization of the equivariant functions that, for instance, include the cross products of the input vectors, like these generalized cross products. And actually, you can see that the generalized cross products of the input vectors are the only extra things that can show up in this parametrization. And this idea that we use to take the classical theory of invariant functions and translate it into a parametrization of the space of invariant functions, of equivariant functions, is something that that can be done in general. And Ben Bloom-Smith and I wrote an article explaining, basically explanatory note explaining how to do that. The main idea is that if we have a group acting on a space B and a group acting on a space W, that action induces an action on the space of maps from B to W. And the equivariant maps are going to be the fixed points of that action. And that's basically what tells you that the knowledge of the invariant maps from B times the dual of W to R give you knowledge on the equivariant maps from B to W. And you can use that to produce an algorithm that, given the invariants on products of the form, allow you to construct the equivariant maps in these spaces. So if you know what the invariants are on copies of your space, or maybe copies of your space under duals, then you can find all the equivariant functions algorithmically. This formulation also can be used to parameterize translation invariant and permutation invariant. And the permutation invariant functions will be expressible as message passing, so you can express them in terms of graph neural networks. I'm not going to go into the details. So finally, I want to show a couple of examples. So this example is a simple example where basically we have this double pendulum connected with springs, and we want to learn the dynamics. And basically, the main observation that we have here is that this system is equivariant with respect to rotations in this plane, but it's not really equivariant with respect to rotations in the z direction because of the gravity. Like if I move these guys like that, then they will not be, the dynamics would not move in the same way. They would not rotate in the same way. However, if we add the gravity as an input to our machine learning model, then what we obtain is going to be equivariant with respect to rotations. And we can think of this as a passive symmetry that had to do with the choice of the coordinate system. Like if we rotate the particles, if we rotate the masses and we also rotate the gravity, it's kind of like just using a different coordinate system for physics. So this is a passive symmetry that we can implement into our model as well. And so for learning these dynamics, we have two approaches. One which is neural ODE, and another one which is a Hamiltonian ODE neural network. I'm not going to describe what they are. I'm sure that many of you already know. But the one thing to mention is that the Hamiltonian neural network incorporates one extra symmetry that the neural ODE doesn't. So the neural ODE learns basically the differential equation, which is given by an equivariant function, and just integrates that. Whereas the Hamiltonian neural network learns a Hamiltonian and integrates that Hamiltonian using this symplectic integrator. So it's already using the fact that the system is Hamiltonian and the energy is conserved, which is another symmetry. And I think that it's nice to show that in these results, you can see that the bigger the group, so the most symmetries that you impose to your problem, the smallest the error is. So the biggest group that we can impose here is O3 by using this passive symmetry, and the error is smaller than using, say, O2 or SO2 or D2 or D6, etc. These groups are finite, and you see like the performance gets worse. And this MLP doesn't really impose any symmetries. And between the Hamiltonian neural network and the neural ODE, this one imposes the energy conservation, and the other one doesn't. So that shows as well that more symmetries are better. So another, I'm actually very excited about this work, but I don't have a lot of time to describe it. So we define units equivariance, which has to do with the fact that when we are learning this dynamical system, we're predicting some energy, which is the Hamiltonian, and this energy has units. In this case, it's kilograms meter squared divided by second squares. And so if we do a transformation in the unit system, then the prediction in the energy should transform in a predictable way as well. And you can actually implement this symmetry by using this idea of you take your input features and then you produce a set of dimensionless features by kind of like constructing features that cancel out all the units, and you can use those features to learn the function and then use a correct scaling to produce your dimensional outputs. And this architecture actually works very nicely and should be able to implement these scaling symmetries, which are complicated because the group of scalings is actually not a compact group. So it's it's something very interesting, and I'm happy to discuss it later. And finally, just want to mention that there is applications of these models, in particular to cosmology, and the people that are working on these are Kate Story-Fisher and David Hogg at NYU, and basically they use these dimensionless scalars to predict properties from dark matter simulations to hydrodynamic simulations, and basically they want to predict the positions of the masses of galaxies and things like that. And basically they use these dimensional scalars to find invariant features from their dark matter simulations, and it performs quite well. So as a summary, I'm going to say that enforcing exact symmetries in machine learning models give you the correct model assumptions. It gives you a smaller sample complexity and smaller generalization error and out of distribution generalization. And in this talk, I just show you how we can use classical invariant theory to parameterize all invariant and equivariant functions, and how to extend it to units equivariance as well, and how there is an explicit translation between invariance and equivariance using invariant theory. And currently, I'm working on extending these ideas to working on vector and tensor images. And these are my references, and this is my final slide. So I don't know if you have any questions. I'm happy to discuss. Thanks.
Hello. I just wondering, so you mentioned a little bit earlier in the presentation that there is some applications of these equivariance functions in relation to graph neural networks. I was just wondering if you could go a little bit more into detail of what maybe some of the applications specifically related to graphs are.
Yeah, that's a great question. So graph neural networks are a particular case of equivariant machine learning, because when you have a graph, there's not a unique representation of the graph as a matrix. So if you're writing your functions as functions of the matrix, then they should be aware that you can do a modification on what matrix you use, and then the function that you learn should be consistent to those changes. In particular, the changes are permuting rows and columns. Just like the order that you use to write the nodes in the matrix is not an intrinsic property of the graph. So then that is what I think I mentioned in the talk, that is a passive symmetry, like a symmetry that is like, there's many ways to express the graph as a matrix. So then the functions that you would write have the property that f of applying the permutation to the rows and the columns implies that either the function doesn't change, or the function, if it's a node embedding, it changes with that same permutation in the output. So it's an equivariant function. So then all the graph neural networks architectures that you see, or most of them, are either 100% equivariant or approximately equivariant, and with respect to that group action. And some people are working on thinking about, if you fix the graph maybe you want to write the functions that are equivariant with respect to the automorphisms of the graph, which is a much smaller group. But yeah. So I guess that those are the two connections with graph neural networks.
Hi, thank you for your talk. I wanted to ask you about, so you mentioned briefly that the non-compactness of the group of scale transformations was a problem. Can you elaborate a little bit more on that, please?
Yes. So a lot of the results that people use that, for instance, the groups are finite. So if you have a finite group, then you can enumerate all the elements, and you have like a finite object. So for instance, that you could do, for instance, data augmentation, and if you want, you could even incorporate all the transformations of the group inputs and outputs. When the group is not finite but compact, you still can do some things because you have like a hard measure in the group. So there's like a measure that is uniform with respect to this group action. But when the group is not compact, then you don't have that. I mean, if you saw in some real analysis course that you cannot have a probability measure that is uniform in the reals, that's basically because it's not compact. So then you don't have like the notion of uniform space with respect to the group action, and that brings you a lot of issues to deal with. I don't know if that answers your question. The fact that you can have like these scalings can go from 0 to infinity, then you cannot have a measure that is uniform with respect to that scaling. And that, yeah, is a little bit hard to deal with sometimes technically.
Yes, thank you. But then on the positive reals with multiplications, that's an amenable group. Is that somehow useful?
Mm-hmm. Yeah. So the fact that it's a reductive group makes it easier to deal with. And there's some tricks from convex analysis that you can use to compactify it and have a uniform measure in the complex plane. Yeah.
But on the real so it's an amenable group in the sense that you can approximate the hard measure with probability measures. Like, is that somehow not possible to do?
So we didn't use that, but I imagine that it brings some simplifications to the problem with that. Yeah, like the same thing. For instance, if you look at the Lorentz group versus the orthogonal group, they're both very similar. The space of invariants are very similar, but the Lorentz group is non-compact because the inner product is not positive definite, but it has very similar properties as the orthogonal group. So even though it's not compact, there's some things that you can do with it that is easy. The issue with the scalings is that since it's not compact, you don't know that the invariant polynomials will generate, like there would be even invariant polynomials. And in the case of the scalings, actually the invariants are not polynomials, but they are rational functions. So they are quotients of polynomials. And that, I mean, it's not too bad. It's just like you don't have invariant polynomials, but you have invariant functions, which are quotients of polynomials, and you can deal with that. But there may be other non-compact groups where the invariants are way more complicated than like rational polynomials. Mm-hmm. Functions, I guess. Yeah.
I'm curious, if you had a problem in which you had all the invariances kind of identified, and you try to learn a neural network, would you learn the same neural network if you tried multiple times? I don't know if this comes from like a sparsity. It's like if you sparsify and the lottery ticket hypothesis, that's where this question is coming from.
Yes, that's a great question. So if you have a generating set that like every function can be uniquely expressed by that generating set, then you expect that you will learn the same functions as if you make it to like training error 0, say, for instance, right? But for instance, in the case of the scalars, that is the case if the number of points is more or equal than the degree of the space, of the dimension of the space, sorry. If you have more points than the dimension of the space, then these polynomials are not independent in the sense that you can write one generator as a function of the other ones. So then you won't find exactly the same functions. They are like over-parameterized in that sense. So I don't know if over-parameterization would be, because over-parameterization is very useful in general. So it's unclear to me if in this context over-parameterization would be useful or not. I believe that it should be useful in the same sense that it's useful in other contexts of deep learning.
Okay, thank you.
Or optimization, yeah.
Okay, so with that, we're going to close this Q&A and give it to Miguel for the closing remarks. Thank you.
Thank you so much for inviting me.